Hi, we are getting back into physics this semester, and we're starting out with chapter 18, which is on electric charge and electric field. So just like last semester, you'll be expected to fill in the blanks as you go along in your class notes and pay attention to any assignments. So as we start out, we're going to start out talking about static electricity. This is when you have electric charges at rest, so not a current in a wire. But static electricity is what's happening when in the wintertime you peel off a wool sweater and you hear that snap, crackle, pop. The static charges build up and then they discharge quickly. So we've got two types of electric charge, as you well know, positive and negative. And when we work with charges, we want to remember two fundamental rules. One rule is that like charges will repel and unlikes will attract. And so that means that if you have two positive charges, they're going to repel. Two negative charges, they'll repel. But a positive and a negative charge will attract each other. And our second rule is that electric charge is always conserved. So what does that tell us? That tells us that you can't produce charge out of nothing, and you can't make it disappear. It has to always be accounted for. And we'll see this in several of our examples. This is the law of conservation of electric charge. Robert Millikan is famous for coming up with a unit to measure electric charge in. He said that electric charge was quantized, so it comes in fundamental packets of energy, and it always comes in a whole number of these fundamental units. He called it charge E. That's the smallest charge that can freely exist. It has a value. And so if we just come down a little bit, let's see, whoops, all right. Maybe I can make my screen go up a little bit so you can see more. So, like I said, Millikan said that charges were quantized. They come in a fundamental unit. The fundamental unit is the charge on the electron, and it is, for the electron, it is a negative charge, so it's negative 1.6 times 10 to the negative 19th coulombs. The unit we measure charge in is the coulomb. Now, if we were just talking about the base unit of charge, it would just be 1.6. You'll see over here I've added O2. We're probably just going to keep it as 1.6 for us, but if I give it to you in writing, you'll use whatever I give. So 1.602 times 10 to the minus 19 coulomb. A coulomb is abbreviated capital C. I almost always will probably try to write it out or at least say it when we talk about it. Like with a lot of things in physics, we don't always use the whole unit. Sometimes it's a multiple of that. And the units that we find most common this semester will be millicoulombs, nanocoulombs, and microcoulombs. So a millicoulomb is abbreviated MC, and it is 1 times 10 to the minus 3 coulombs, or 0.001 coulomb. Remember that when I give you a decimal point, I'll always, if there's no number in front of it, I'll always give you the leading 0. So you'll be sure to notice the decimal point. A nanocoulomb is 1 times 10 to the minus 9 coulombs. So as you can see, it's a teeny tiny amount of charge. A microcoulomb is 1 times 10 to the minus 6 coulombs, and again, a very small amount of charge. So millicoulombs are MC, nanocoulombs are NC, and microcoulombs are μC. This funny little symbol that looks like a U with a leading tail is a lowercase Greek letter mu. All right, moving right along. So let's talk about some of the charge in the electron. I'm sorry, charge in the atom. Got ahead of myself here. So all electric charge has its origins inside an atom. As an example, this is meant to be a neutral carbon atom. So it would have 6 protons, 6 neutrons, and 6 electrons. The protons and the neutrons are held in the nucleus. Protons have a positive charge, neutrons have a neutral charge. We'll talk about them more later. And then the electrons surround it. Now, in this drawing, they have the electrons in the old-fashioned sort of tracks, where you have the 1s2 and so on coming around it. You have the orbitals. But in reality, we now believe that instead of being little tracks like at a racetrack, you have orbitals that are more like balloon-shaped or cloud-shaped areas, so regions. So our electrons are in the electron cloud, and we do believe the electron cloud has regions of higher probability and regions of lower probability for where you would locate your electrons. And they're not usually considered racetrack form. All right, moving along. So we know that the nucleus holds the positive charge that's attached to the protons, and that the negative charges surround it. So to have an ion, what happens is that it either gains or loses electrons. Your atom, if it adds electrons, it becomes negative. If it loses electrons, it becomes positive. So the strength with which a nucleus can hang on to those electrons can be relatively complex. But this strength determines how easy it is to make a particular kind of ion. We have something called the triboelectric series, and we'll look at this in lab number 1, where we look at the relative ability of certain materials to hang on to electrons. So, oops, I overshot. My apologies. I got a little carried away. So if we look at our graphic, and this will show up in the first lab as well, you can see that rabbit fur forms a very positive charge, and that means it gives up electrons easily. Rabbit fur just donates electrons like crazy. PVC pipe is very negative on our series, and what that means is it hangs on to electrons, and in fact it'll hang on to its own electrons and even grab a few extras along the way. And you can see the ones in the middle are kind of neutral. So the closer it is to the positive end, the more likely it is to form a positive ion. The closer it is to the negative end, the more likely it is to form a negative ion. So if we look at this, we look at our relative positions. Suppose you have a glass rod and a piece of silk, and you rub the glass rod with the piece of silk. We'll do this again in the first lab if all goes well. What's going to happen is we look at it. The glass rod is down at the positive end, and the piece of silk is to the right of it, which is towards the negative side. So the rod will become positive, and the silk will become negative. Suppose we pick a different kind of rod. Suppose we have a PVC rod and a piece of silk. So the PVC rod hangs on to electrons. It's going to become negative. And the fabric, well, the fabric becomes the opposite of whatever the rod is. So if the rod is negative, the fabric is going to be positive. Right? Other examples we don't have written down. Suppose you had wool and cotton and you rub them together. Maybe you've got a cotton shirt on and a wool sweater. If you pull that wool sweater off, you can see the wool sweater is going to be positive and the cotton is going to be negative. Suppose you have a polyester blend shirt on and you rub a styrofoam cup on it. The polyester is going to become positive and the styrofoam cup is going to become negative. Okay, so it's all about how close is it to the positive, which one's closest to the negative side, which one's closest to the positive side. and it's related to the way they hold on to electrons or donate. Let's look at something else that's fairly common in our world, and that's a water molecule. So a water molecule, H2O, one oxygen atom and two hydrogen atoms. Now, if you were drawing a water molecule and didn't know any better, you might say, okay, I've got a hydrogen on one side and an oxygen in the middle and a hydrogen on the other side, and they form a straight line. But that is not the case. In reality, the two hydrogens are not 180 degrees apart, they're only 104.5 degrees. So they're sort of bent towards each other. And this unique configuration actually makes water what we refer to as a polar molecule. We're not talking about the bonds. We're not talking about ionic, covalent, and polar bonds. We're talking about the physical shape of the molecule creating a charge distribution. So the hydrogen end will end up being more positive and the oxygen end will be more negative. And we'll look at that in a second graphic here in just a second. On a damp day, it's really difficult to maintain static electric charges. We do demonstrations with this in lab. If it's one of those dreary, rainy January days we sometimes get, what you will discover is that it's going to be very difficult to get our rods to stay positively charged because water in the air will attract the extra electric charges. So here's the second graphic where you can see hydrogen has one proton and one electron. So the proton is in the nucleus, but the electron, because the hydrogen is bonded to the oxygen, the electron is over here closest to the oxygen. And here's our second hydrogen atom, and its electron is over there as well. So you can see that the oxygen side of a water molecule has lots of electrons, and the hydrogen side doesn't. That makes the hydrogen more positive, the oxygen more negative, and the result is that we call it a polar molecule. What's cool about a polar molecule is you can actually demonstrate this using a charged object. So in the drawing on the left, you have a spigot, and here's a stream of water with the plus representing the hydrogen end of the water molecule and the minus representing the oxygen side of the water molecule. And suppose you have some sort of plastic charged object. In class, I have been known to use a ballpoint pen. I've got hard plastic rods. I've got all kinds of things. But you take your rod and you give it a charge by rubbing it either with a piece of wool or a piece of fur. And what will happen, if the rod is positive, it's going to attract the negative side of the water molecule. So that would be the oxygen side. And you'll be able to lift a stream of water by bringing this charged rod close. We'll try to do this in lab. But again, we're at the mercy of the weather. If the weather is really damp that day, we won't be successful. And this is a photograph of a stream of water from it looks like a kitchen faucet and just a plastic comb. And what they've done is taken that plastic comb and rubbed it vigorously either on a wool sweater or a piece of fur or even a piece of polyester will work. A lot of things can make that plastic comb have an electric charge on it. And it doesn't matter if the comb is positive or negative. If the comb is positive, it'll attract the oxygen side of the water. If the comb is negative, it'll attract the hydrogen side of the water. So regardless of the charge on the comb, you're going to be able to bend that stream of water. It's a really neat phenomena, and I hope you get a chance to try it. And that gets us to Coulomb's law, which we're going to save for a different video. So I'm going to stop my share, and I'm going to stop.